In this video, I'll be doing a coding ride-along on how to power this curious and useless but fun contraption. It assumes that you have at least some coding background and may or may not have used kOS before. However, most kOS and coding skill levels should be able to glean some useful information from this tutorial. There have been some other good introductions to kOS before, but the way I use kOS does seem to be substantively different from any other projects I have seen. So I felt it would be good to explain some of the basics of how I'm approaching problems in kOS before delving into the more specific topics like the power of vectors and the mechanisms behind egg ships and tumbleweed rovers. kOS is not highly performant and is hard-capped at a fixed number of operations per physics cycle, so a lot of the coding style I've developed revolves around trying to make the best of the limited processing power available. And while I feel I know quite a bit about kOS now, I do not by any stretch feel I have mastered it. Ideas are always welcome in the comments. I'll be running this as a coding session where I start from scratch and build the code as I go, while also providing commentary and instruction. If you're already very familiar with kOS, I would recommend skipping to minute 7 where I get down to coding. If not, I'll provide a brief introduction to getting started with kOS. If you're completely new to kOS, the easiest way to get started is to install it via CCAN. So here I've got the CCAN application open. Do a quick search for kOS. Come down here and then click this and hit apply. It's going to handle all the installation for you. If you have kOS installed, you'll have access to the kOS processor parts. These are in the command and control section and are referred to as scriptable control systems. So you can see there's multiple ones, but they're mostly technological levels. I'm mostly playing the end-game kind of technology, so I use this Cal 9000 almost exclusively. It's fast, it weighs very little, and it's small, so you can effectively just stick it anywhere. I've put this one right here. There are a few options you can set on these parts. I don't typically set much of anything except the boot file, which allows you to automatically boot a script when the craft loads, which can be very useful during development. That's a subject I'll probably touch on at a later date. So this is the sort of contraption I'll be using for the rest of this sort of code walk along here. It's really just a big giant batch of pistons in a grid. So we can move them up and down, change their traverse rate and damping at will using kOS. And there's no particular order or size. This one has over 700 parts, so if you're working on a lower-end processor, you might use fewer or use fewer of these panels on the sides, whatever you need to do to make it work on whichever system you're using. I'll put the link to the craft file in the description below, but feel free to take some of these off if needed for performance reasons. And most of the rest of it is just solar panels. I am using some graphical mods here, so it might throw some errors at you saying certain things are not installed. You should be able to safely ignore those and move forward with the craft because they're all graphical enhancements other than kOS. I tried to stick to stock breaking ground parts here. Okay, and here we have the contraption we're going to be using. Got all our pistons that can be controlled. We can change traverse rates. We can do all of the necessary adjustments. And the first thing we're going to need to do is open up a kOS terminal. And there's two ways to do that with kOS. One, you can come over here to the right, kOS button, and it's going to give you a list of every kOS processor that's available in your game at that moment. So I've started with a clean game for this. So they're really just the one, but if you click on this button here, you can bring up the terminal. And the other option is to come to the kOS part that you added. Like Cal 9000, you can right-click on that, open terminal from there. Increase the font a little bit here. Alright, so now I have an open kOS terminal. You start off in effectively the file system, and you're on the file system of the kOS processor itself. And most of my scripts, I keep those out on my file system, which in kOS, you want to switch to the archive to get to your local computer file system. So I'm going to do that by saying switch to 0. And now if I look for files with a list command, I can see a lot of them, because this is where all of my kOS projects are. Now, the way to find the file system out on your real computer is to come out and find your root KSP directory. If you're using Steam, you can right-click and say Browse Local Files. And once you found your root file system for the Kerbal Space Program game itself, go to the Ships, Script, and now this is the equivalent of the archive. This is the equivalent of that Switch to 0 folder. And then I'm going to be working out of this tutorials folder, so I'm going to change my folder here to be and now I can see just the two files that I expect to have there. So you can run almost any kOS command out of this console here. So for example, if I do this, I'll be able to see what my velocity is. Velocity contains both an orbital velocity and a surface velocity, and the print statement is just going to show me both. Sometimes the print statement's very smart, and sometimes they're not. Now, my tool of choice for working with kOS is Visual Studio Code. And that's because it has a very good plugin for kOS. It does syntax highlighting and all the things I'm used to and all the languages I'm used to. So I'm going to briefly describe this template because this is what I've settled on as my core starting point for almost every kOS script that I make. And it's based on a lot of trial and error building things that are performant. And most kOS scripts that I've seen operate in a sequence of events, right? Like a launch script, you'll have a stage for the launch, and then it will do that going straight up until a certain altitude, and then it'll say, turn and change your throttle or stage. And it'll just be this sequence of events which have nothing to do with each other, and they pass one another and never go backwards. And that's more of like a scripting language. And what I do is much more of shifting from mode to mode rather than a sequence of events. And the script is based on doing that. So the first thing at this top script here is this @lazyglobaloff. And @lazyglobaloff tells it to not allow me to accidentally create globals. In other words, I have to declare absolutely everything with a declaration statement. Local or declare global. And if I just do a set statement on something that doesn't exist, it's going to fail. And that helps prevent a lot of accidental errors from typos and everything else. So it's just kind of a code safety. kOS does not have any real true constant. Everything can be changed. But sometimes I do want them, so I just designate them in all caps. And I don't use constants as much as I do in other languages because in kOS it lacks a lot of optimization. And optimization is key. You don't have a lot of performance in kOS, so I have to be much more cognizant of performance as I write code. And so using a constant requires it to make an access statement every time it looks up this constant, which lowers performance, so oftentimes I'll just use true values in line. But occasionally there'll be a value that I use all throughout the code that I want to change quickly. Makes it worth the hit. So these two here are kind of the core of the looping mechanism. So ship mode ref is a reference to a function which is going to do whatever the current ship mode is. And then I just call the ship mode ref, and it's going to call whatever the base ship mode is. So right now it's set to do wait, which is a function which does nothing. But when I shift it to a mode that does something, it's going to execute that down here. And the reason I do this is because, I could do everything off of ship mode and do some like ifs and elses, but those suck up performance, and if you have a lot of modes, it can suck up a lot of performance. So I don't want to do that, waste performance and precious cycles on things that I don't need to. And then this is just a way to show myself visually what mode I'm in. So these two have to be kept in lockstep. In the program is just the primary looping mechanism. So if you set this to true anywhere in the code, it's going to exit out of the primary loop and go into the cleanup function. And then show arrows. Vector drawing can be somewhat performance intensive and can degrade performance over time. So I like to be able to turn arrows on and off, real and live in the code so that I'm not eating that performance hit all the time. I usually have a find parts function which gets called right off the bat, and the reason for that is that in kOS the name of the performance game is cache. And you don't want to be looking up a part every single time that you use it. So I'm going to go find every single part that I want to use throughout the entire execution of the code right on startup and never look it up again while I'm working live. Inside the main loop, I have this handle input, which just loops over and over again looking to see if you've pressed any button. If you have, grab that button and decide what to do with it. Print control data, I try to keep all of my print statements here in this little section, and that helps make it easier to format, and print statements also have performance implications, so I try to print as little as possible, and this kind of helps me see exactly how much I'm printing and can turn things on and off as I need to debug certain statements. This seems a little bit odd because it's a wait 0, which should do nothing, but in kOS it does actually do something very specific. So kOS runs in sync with the physics ticks, physics updates of Kerbal itself. So whenever a physics update happens, it then kicks off kOS, and kOS is going to keep running until it hits a wait statement. So what this is saying is, when you hit, you have your physics tick, and then you kick off the code, and then you execute the code, this wait statement will say, okay, I don't want you to do anything else on this physics tick. I want you to wait until the next physics update to continue. And that way it's not doing a lot of unnecessary extra computation. And it also helps ensure that the world and the universe is not changing while you're doing your code. So if you execute all of your code within a single physics tick update, then nothing changes for the entire course of the execution. But if you end up bridging your code execution across multiple physics updates, then you end up in a situation where your velocity is changing, your position is changing in the course of the execution of your code, which can cause unexpected results. So I'm going to do a live coding session and create the script powering the behavior you saw at the start of this video. I'm going to explain what I'm doing as I go along. This isn't really meant as a true introduction to coding. I assume you know at least a little bit, but I think anyone at any experience level that is following along will be able to learn some things from this. So the first thing I'm going to need is to go find all of these pistons that I'm going to be interacting with and cache them. So first thing to place to put them. Now a list works as both an array and a list in kOS. So it's a convenient way of storing multiple items. When down here, I'm going to create the code to go find it. So I want to be able to see that something is happening. Sometimes this can take a few moments while you have a lot of parts going. So give myself a little indication that things have started. All right, so I'm going to find a list using some of the kOS part search functions. And the one I'm going to start with is called parts named. And a name is like the name for that particular kind of part, like it's this type of piston or this type of cockpit. And the easiest way I've found to go find what these names are is in kOS. You can come and right-click on a part, and you can go down to this section where it says change name tag under kOS. And you can put a tag on it, which gives it a unique identifier, which you can search for. But it also, inside this window, contains the name of the part. So if I go do a So it found 62. These are all zero-based indexes, so I have 62 of these pistons here, which matches exactly what I would expect. And that was using this ship parts named piston. Now the tag, show briefly that, I can use the parts tagged function. It's not case sensitive here. Okay, and now I can find this one exact piston. So now that I have this that I can use, okay, so now I have an array that's going to be like that. But in kOS, if you want to manipulate a part, you also have to go find its corresponding module. Now, finding modules is a little bit tricky here. So I'm going to use this unique ID I just created to go module hunting. So it's tagged unique ID. Let me get the first. This thing gives me a list, so I need to grab the first one off of it and then go find the modules on it. And sometimes you have to kind of go through and figure out what each one of these does, but I've already done that process, so I know it's this one, which is going to let me control the piston. And so I'm going to go say get module. Okay, so now I have a bunch of actions on here. So you can see target extension is a settable value, and we have events that are callable. We can extend, retract. The primary ones we're going to be doing are setting traverse rates and extensions. So now I have a list of these piston parts, but I'm also going to need the modules, and I'm going to need the modules and the actual part co-located in an easy way that I can look up both. So I'm going to do that by creating a lexicon. So I'm going to loop through this piston parts. And for each one, I'm going to go grab the piston module. And I'm going to use these set field values that we saw here, and I'm going to set some defaults for the initial startup. I could go pretty quick at the start. Default damping, and then I'm just going to set everything to an extension of 0 to clear the board at the start of the kOS script. So this pistons, this was the thing I created up here at the top to store all of these. But I'm going to add, rather than adding a module or piston, I'm going to add what's called a lexicon. And the lexicon is a set of key value pairs. I've heard it called dictionaries in other languages as well. And this will give me a convenient way of co-locating my modules and my parts. And yeah, I think that should be good for now. So now I'm going to add this lexicon to my list. I'm going to test it out here in a moment, but I'm going to add a couple quick sanity checks to make sure everything is getting found the way I expect. Okay. I'm going to stick a wait statement here so that this doesn't get eradicated before I can even take a look at it. I think it's time to go test it out. Okay, there's the file I'm working on, so I'm going to run it. Okay, I appear to have an error. Parts name. Parts named. Okay, so we have everything we kind of expect there. Now I can turn this guy off for a minute. Now it's time to go do something with these parts. So first thing I'm going to do is create something that just randomly sets them. And I want to have it change that on a regular basis. So I'm going to create a timer for that. And I'm going to need another value here to hold my timer and make it persistent. So these variables I'm sticking up here, they say local, but they're effectively global to everything in this file. They won't be global to anything outside this file, but in any of these functions, if you declare it at the root level, it can be accessed. But anything that you declare inside of a function, for example, this guy, will not be accessible once my loop is completed, and this won't be accessible once find parts is completed. So they are local to the scope of the function or the loop. So now I have a timer value that I can use, and that will let me keep time and do things on specific time ticks or physics. So I'll change one of my preset modes here. And time seconds. Okay. So this is going to say every 5 seconds do something, otherwise do nothing. So I'm just going to loop through every single value, or every single piston, and set it to a random value. So every piston can go to a max of 4.8. I only want to set it to half of that, and I want it to be somewhere in between 0 and half of 4.8. So this random gives you something which is between 0 and 1, with many variations in between. So this statement will give me something between 0 and 2.4. Now I think we can go test it out. Took a little bit, and that's because my initial timer was blocking it for the first 5 seconds. So I'll go fix that. All right, there we go. So that's working just fine. So the next thing I want to do is show you how things are stored in this list. And this guy will loop through all of them, but is it doing it in any particular order or useful order? So once again, because I'm maintaining state across multiple executions of the script, I'm going to need somewhere to hold that state. Start up here. I want to reset this thing. So right off the bat, I want this thing to stop doing anything once it has fired every single piston. I'm trying to fire them in order of the loop, and I don't want to have any kind of issue when it goes over, and once it's done, I want to change my mode back to doing nothing. And I think I go ahead and use a timer value here. So make sure it fires on the first round. I want this one to go rather faster. So I'm going to set it to something aggressive out of the gate. So you can also access, we did the for loop here, where it's going to loop through everything. You can also access every single value in a list with its index using this bracket notation. And this value here, this comes from our lexicon, where I put it here. So these will match up. I'm just going to set it to half value by default, and I need to move my iterator up one on every execution. All right, should be worth a try. Okay, so that's working. So you can see there is kind of an order to all of this, but it doesn't actually make any kind of logical sense. It's not a useful order that we could interrogate or try to determine where a particular piston is in space based on its index. So, in large part, I'm going to be using the piston's actual position in space to control it. Now I also want the ability to perform a clear. Simply reset the board. And I want the clear mode to actually move into wait once it's done. So I just wanted to do something very quick. And then go back to wait rather than creating an entire mode for itself. So since it's not a mode, I'll just do that. Test out my clear mode, and it works quite well. But I want kind of a nice little dramatic fade, so I'm also going to create a function which can change the traverse rate. And this time I'm going to use a parameter. So these functions can take parameters. And on my clear, before I clear the board, I'm going to set it to something fairly low. And since I don't want this to affect my other modes, I'm going to set them to something a little bit higher. And these are not strings, so that doesn't make any sense to do. Alright, so let me give that a try. Okay, there's my random, there's my iterator moving at speeds I expect, and there's the clear board with that nice slow fade to it. Now it's time to do something a little bit more complex. Create a new mode just like I was doing before. And I think I want another timer for this one. Okay. So at the start, every single time, I want to clear the board. Actually, that's not quite true. I only want to do that if my timer val says to do so. Now, I want to find a random piston, which is going to be the principal piston that I use for the peak of the mountain. So remember, this gives me a value between 0 and 1, and I'm going to multiply that by the piston's length. And lists are a 0-based index, so the first value is always a 0. So I'm going to use the floor, which means round down always. So it's going to take a random piston between 0 and 1 less than the max length of the entire array. And I also need a randomized height, so this is going to give me something which is between 1.4 on the bottom end and 4.8, which is the max height of the pistons. And once again, I'm going to look it up based on this random index. Go find its module. Actually, so there is one thing I need to do here to make this a lot more performant. So, back at my Lexicon, so there's one more thing I need to do to make this process a little bit more performant. So back at my Lexicon, I had these values here, but now I'm going to create a map of new values that are going to be updated on the next cycle. setting fields on modules is relatively heavyweight, so you want to avoid doing that as much as possible, avoid oversetting things, and certainly having to look them up again. It's much faster to do it if you already have it in memory. So I'm going to add a couple of things to the target extension here that I'm going to need to make this mountain concept work. So now I have one value which tells me what it was last physics tick, and this is going to tell me what I want to set it to for the next one. And then I can apply all of that in one go. So this is going to set my top mountain's extension updated to this. But now I still have to have a way to get this to represent the actual target extension set field. So I'm going to create a function which is going to apply these target extensions to my actual pistons. So this is going to loop through every single one of my pistons and look at the target extension value and the current extension value. And if they don't match up, now it's going to go and make the more expensive call to set the target extension, and then it's going to update its current target extension to the new value. And you can see here, it started set cache, cache, cache. This is a case where this particular value ends up getting used multiple times. So it makes sense to stick it into a cache value here rather than force it to do this lookup every single time. And this is a pretty simple lookup, but even so, kOS does not give you a lot of performance out of the gate. So these little things add up, especially when you start doing them in a loop of 64 values. I think this initial clear board, I think I'm just going to do that right at the start. And then I think another one of these types of functions for clearing out every single value. Alright, so I'm going to go and see if all this code I just added is actually doing what I expected, which should be to just move one single block. We have an error. Can't quite see what the error is. Target extensions updated. Alright, so I have a typo here. Okay, so it moved one block, and every 5 seconds I should see another one move to a random height. Yes, okay. That's working just fine. Now, for the next complicated part, to make it a mountain, I need to raise all the other blocks up around it. And to do that, I'm going to use Recursion, which is supported in the kOS language, and is very useful for this type of operation. So I'm going to need one other item down here in my lexicon to be able to do this in a performant way. And that's going to be a list of the neighbors of every single one of my pistons. So one thing I want to do now is figure out exactly what the distance between two of these pistons is. So this guy I set a tag. Let's see. Give him a new tag of piston 1. Change this guy to a tag as well. So I can find these guys again. Okay. So every single part has a position, which gives you the position in space, and this is going to be relative to your control part. So this is going to be relative to my CPU core, which is right over here. And then I can look up the position of piston 2 as well. That's going to give me its position. So they're very close, but slightly dissimilar. So now I'm going to get the vector to find the distance between the two. I'm going to grab the vector between those two parts and then measure its magnitude, which is the length of that vector. And if that doesn't make a whole lot of sense to you just yet, don't worry too much about it. I will plan on doing a whole one of these around vectors and how to draw them and how to understand them, how to use them in kOS at a later point in time, because it's a interesting and very complex and very powerful subject, which is, I think, easier to understand intuitively than people might guess at the start. So I'm going to try to take these two values and give me a new one, which has one position subtracted from the other. All right, so I have a new vector, which is the vector that is between these two. And if I grab the magnitude of this new vector, I now know that it appears that these two parts are almost 1 meter away from each other. And so I want to find every single piston that is in kind of this 8 square around it. So I know now that these are going to be roughly 1 meter from each other. And I don't want to get anything that's 2 meters over. But these corners will be slightly further out than 1 meter, but less than 2. So I can safely say that, anything between about 1 meter and, say, 1.8 meters for safety purposes should get me everything that is immediately surrounding this particular piston. So I need to add a new place to hold these new neighbors. And the neighbors are going to tell me in a cached way which pistons are around the other piston. Now, kOS has the for loop, which is very convenient looking like this, but if you want to do a traditional for loop, which has a numeric iterator, which increases with each loop, kOS has a really funky notation with this from statement here, which I often have to go look up because it's so different from any other language I've used. So this is going to loop in here, and it's going to change x up by 1 with every single loop until it reaches the max length of the pistons. Find the current part I'm looking at, create a placeholder for the new array of neighbors I'm going to be building. I'll change this guy. Oops. So I'm going to do 2 loops. I'm going to loop through every single piston on the board, and that piston is going to loop through every other piston on the board and try to find anyone that it would consider to be a neighbor. And it's doing this to exclude itself from that neighbor list. It finds that it adds that index value into the piston neighbors array and then sets our lexicon value to that. And I want to do kind of another sanity check here. To make sure this is doing more or less what I expect it to do. So what I should see is that I should have a lot of pistons which have 8 neighbors. The ones on the edge, I should see quite a few with 5, and there should be 4 which just have 3 neighbors. There should not be any other number inside there besides those values. And that does appear to be more or less what I'm seeing. So I can kill my wait statement again, because I don't need that. Okay, time to go apply that to our mountain. This is going to be a function that calls itself and sets all of the neighbors around a particular piston to come a little ways up, but not all the way up. And then by recursively calling it, I can create that kind of stepped effect of the piston sizes getting increasingly further down and create that form of mountain. So I need a bunch of parameters to make this work. The drop-off is going to represent how quickly I want the mountain to fall off, so it's kind of a steepness rating. And the threshold is going to be that minimum value before it stops bothering to try to map new terrain. So it's going to loop through every single neighbor of this original piston, which is passed in. So I'm adding this right here to make sure that it's not updating and updating and updating, and then it only bothers to update the neighboring piston if it's going to raise it, but it will never lower it. And then the last step, since I want this to cascade downward, is for it to call this function from inside this function for every one of the neighboring pistons. I want to utilize my drop-off to make sure it's smaller every single time. And then the drop-off itself and the thresholds are simply passed on. And finally, so I updated my mountaintop height. Now I need to call my recursive mountain mapper. Okay, let's see what I get out of this. Working pretty well. Should see another one pop up after 5 seconds. Okay, now it is a little bit sort of stale and clinical looking, so I want to add a little bit of randomness in my recursive mapper here. So this will give it a 10% up or down randomness, and see what that looks like. Yeah, there we go. Okay, so I think we can call the mountain done. Now it's time to make it do the wave. Back up at the top. So with the wave, unlike what I've been doing before, I'm now going to be specifically targeting places inside this board that I want to move. And remember, my index doesn't tell me anything useful about where I am in space. It would tell me how to move a particular part. So I'm going to measure this based on the distance from my probe core. So I'm going to keep track of what part of the board, based on distance, should be performing the wave, and then make that part wave, but reduce everything else down. So, to do that, I'm once again going to need to be able to track my state. So, so I need it to loop through a fixed wave distance. And that means I need to set it up here. So I'm going to start by waving from this side going this direction. And I'm using 13 as my base because that's a rough guesstimate on the distance from here to here, because I know each of these are roughly 1 meter apart. And when it reaches the bottom end of the wave, it should start again from the far end once more. Now this value here is going to control the speed at which the wave moves. And this is going to give me the value between these two is an indication of should that piston fire or should it not. And this is going to give me a cached local version of where my control part is in space, which I can then use as the comparison basis to get the length of distance between the piston and this part. So once again, finding the distance using that same algorithm that I used before. And this will be the high point of the wave. And I'm going to utilize that same recursive function to make my wave a little bit thicker with some drop-off. So let's drop off a little bit faster than the mountain. And that doesn't look right. Contoural. Forward position. No, that's not good. Alright, let's see if I can get something out of this. No. 115. Not doing anything because I forgot this necessary step down here to apply the map that I'm updating. Okay, so now it's basically doing a wave, but you can see it's not quite clean. And if we look at it from the top, it has almost kind of a crescent pattern to it. And that's because it is measuring the distance from this control part outward. So the distance from here to the corner is going to be a little bit longer than the distance from the part straight ahead. And that creates that kind of disjointed shape to it. So we want to fix that. And what I want to do is to only measure the distance from here, my control part, to the piston along this axis, but never along this axis. So I'm going to use a function called vector exclude to make that happen. Well, I should say, before I do that, I have to figure out which vector it is that I want to exclude from this vector here. And I want to find a vector which is coming straight out, straight sideways from my control part. I'm going to do that using something called vecdraw, so I know what I'm looking at. And I'm just going to go grab a random example. So vecdraw gives you a way to visualize what your vectors look like in space, where they're actually pointing, where they should be going, and it helps immensely to use these to gain an intuitive understanding of what vectors in kOS actually mean. So I'm going to start, this means I'm going to draw from the center of my ship, which should work just fine. And there's various vectors which are reference vectors for your ship. There's the 4 vector, which points in the direction that your ship is going. And then you also have star and top vector, which point out of the top of your ship or the right side of your ship, respectively. And it's going to be either the star or the top vector that I want, but because this probe core is kind of round, it's not really obvious looking at it which way is the star vector and which way is the top vector. So I'm going to draw it to figure out which one I need. I'm going to try the star vector first. I'm going to draw that and see where it lines up. I'm going to turn on my arrow. Okay, so it looks like the star vector is in point of fact the right vector. So I want to be measuring the distance along this axis, but I don't want any part of the vector which is pointing in this direction to be part of my distance calculation. So now that I know it is the star vector that I want to exclude, I can come in here and exclude it. Use the vector exclude function. Now, since this is not going to change over the course of execution, I'm going to go ahead and cache that before I get into my loop. Okay, now let's give that a go. Okay, so it seems to be working. I now have a nice clean wave. So the last thing I want to do is show you how to interact with other vessels. In this case, the vessel is going to be Bob. So I'm going to go ahead and, well, I need to flatten that out for a moment. There we go. I'm going to get Bob out of his seat here, because we won't be able to find him in space until he's not part of the current ship. All right, Bob, you intrepid little Kerbal. Out you go. Okay. So Bob's going to be my target. And I'm going to cache him again because I don't want to take the hit for finding him in space every time. I'm going to create a new mode, which is going to be a Kerbal Trap. I want everything to move very quickly here. Yeah, go ahead and clear the board too. Okay. Alright. So the first thing I want to do is make sure in the execution of my loop here that I have actually found Bob. So I'm going to check at the start to see if my Kerbal target equals 0, which was the default from up above. And if it is that way, Now, kOS does not have any form of exception handling, so if Bob is not actually out there when he moved to the Kerbal Trap, this is going to fail and it's going to cause your code to halt. A safer way to do this would be to get all vessels, and there's an API call to do that, and loop through all of them looking for the name. But I'm going to keep things simple here. I'm going to get his position in space, so that once again I can be measuring distance off of it. I'm going to need to also do another vector exclude here, because I'm going to be measuring, to create my Kerbal Trap, I want these walls to go up when he gets close, so I need to measure the distance between him. I'm also going to raise him up, and so the distance between him when he's raised up versus a closed piston could be quite large, and I only want to measure the horizontal distance and not the vertical distance. So this time I'm going to be excluding the 4 vector of the ship, the one that's pointed upwards. I'm going to exclude my ship up 4 vector, from my vector to my Kerbal. Create an arbitrary threshold here. Sure I clear my target extensions at the start and apply them at the end. Okay, so this should, if the piston is within 1.5, it's going to raise the Kerbal up if it's an interior piston. But if its neighbors are 8, then we know it's a piston that's on the inside. So this will create a wall around the outside, and this will create a walking surface for the Kerbal to walk on. Anything that's not close, I want to just go ahead and set that to 0. And I suppose this would actually be redundant, because everything will end up getting set to 0 over time. So let's see if this works. Okay, so it's moved up. Let's walk around a little bit and see if it gives him some blocks. See if we have a wall at the edge. There's our wall. Okay, so he now cannot fall off. He can't get down. He cannot escape. We have a very effective Kerbal Trap here. If you've stuck with me here to the end, I hope this was informative and useful for you. Let me know your thoughts and feedback in the comments below. If you'd like to see more like this, please give the video a like and the channel a subscribe. I intend to do at least a couple more sessions like this around kOS topics, so if there's something you'd like to see, let me know. Thanks for watching.